Alright, so in the last video we just kind of talked about how certain kinds of linear combinations of functions, if they get plugged into a linear differential operator with constant coefficients, you'll get another linear combination of the same functions. So polynomials get taken to polynomials through L. Exponential functions get taken to the same kinds of exponential functions. Combinations of the same kind of sine and cosine functions will get taken to another combination of the same sine and cosine functions. So that's what we're going to use in this general method. Is given our equation, we want to identify, basically by looking at phi of x, and sometimes having to look at the structure of L itself, but usually just in phi of x, a list of functions that will allow us to do two things. We want to be able to write phi of x as a linear combination of those functions, while at the same time write y of p as an abstract linear combination of those functions, meaning with some constants that we don't know what they are, some coefficients, some undetermined coefficients. So that when we plug y sub p into the operator L, calculate what that is, group the like terms together, what we get is another linear combination of the same functions. So as long as we can do these two things, then our general form of our guess, y sub p, is the right guess. We just have to figure out what those undetermined coefficients are. But the idea is this equation really just turns into an equation comparing two linear combinations of the same set of functions. And because they're linearly independent functions, the corresponding coefficients for each term have to be equal to each other. So that's going to give us a bunch of equations, a system of equations involving all of our undetermined coefficients. And we'll just solve that system of equations, and then we'll have exact numbers, which will give us an exact representation of our particular solution, y sub p. So let's see this in action in some examples where phi of x is just a polynomial. In this case, we're taking a very simple example just to illustrate how we do this. In this case, it's going to simplify very easily. We have a third order equation. Our phi of x is x squared. So it's a polynomial of degree 2. So we want to think of it as a general linear combination of the functions x squared, x, and 1. So the coefficients are 1, 0, and 0. Now we want to write our function y as a similar kind of combination, except in this case, because y does appear in our equation, if we imagine that y is a quadratic function, then the third derivative is actually going to be 0. But it doesn't matter. It's some lower degree polynomial. So if I add a quadratic to a lower degree polynomial, like a linear function or a constant, I'm still going to have a quadratic. And it makes sense that we have two quadratics equal to each other. So in this case, the 0th derivative, which is y, is the lowest derivative we see in the equation. So that's what we need to do, is set y sub p equal to the same kind of linear combination as phi. So it's a quadratic. We're just giving these undetermined coefficients, ax squared plus bx plus c. And then we plug it in. We plug that function into L of y of p, or figure what that is. The third derivative is 0, so that's all I'm illustrating here, is the third derivative is 0. In other examples, it might not be 0. You'd have some other expression here involving the constants a, b, and c, and the variable x. And then we add to that y, which is our ax squared plus bx plus c, and in this case it simplifies very easily into ax squared plus bx plus c. But in other examples, you'd see that you'd have to combine like terms, and your coefficients for x squared might depend on one or more of those letters a, b, and c, and so on. But the point is, once you have simplified what your L of y of p is as a same kind of linear combination as phi of x, because our equation is equating those two things, we're just going to set them equal to each other. So these two quadratics have to be equal, but the only way two quadratics can be equal is if they have the same coefficients. So ax squared has to be equal to 1x squared, so a is 1. bx has to be equal to 0x, so b is 0, and c has to be equal to 0, which is so c is 0. So that tells us that our solution, particular solution, is just y sub p equals x squared in this case. Remember, these two things that we have here, these are the two things we mentioned before. We had to be able to write phi of x is a linear combination of some functions, so that L of y of p is also a linear combination of those functions, so that we can actually compare the two. Let's look at a little bit more complicated example. In this case, we have a second degree, or second order equation, I should say. Phi of x is x, which is a linear function. So in general, a linear function has two terms, an x term and a constant term. So we've written phi of x as a linear combination of these two functions. In this case, y prime is the lowest derivative appearing in our equation. So we have to let y prime be a linear function. But if y prime is a linear function, then the antiderivative of that is a quadratic function. So our guess, y sub p, should be a quadratic function. And notice I only have two terms here. Because we're only going to have two terms, so we have two functions that we're creating our linear combinations from. So we don't need a constant term here. Because if I have a constant term here and I plug it in up here, that constant term, no matter what it is, turns to 0 because the derivative of a constant is 0. So in this case, we only need the x squared term and the x term, because when we differentiate this y sub p, we will get a linear function, something times x plus a constant, and that's what we needed in this case. So if I plug y sub p into our operator, which is just y double prime plus 3y prime, the second derivative of this is just 2a, so that's what y double prime is, and then plus 3 times y prime, which is 2ax plus b. Now I just combine like terms, and I get a linear combination of x and the function 1, which I can equate to the same kind of linear combination for the function phi of x, which is just x. So writing those equal to each other, we just have to match up the coefficients. 6a is the x coefficient, that has to equal to 1, and the 2a plus 3b has to be equal to 0. So we get a system of equations involving our two undetermined coefficients. And if you do it right, what will always happen is you'll have the same number of equations as you have undetermined coefficients. So you'll always find a unique solution. In this case, a equals 1/6, b equals 1/9, which we plug that back in to our formula for y sub p up here, and that gives us a particular solution. That y sub p is x squared over 6 minus x over 9. And you can always check and plug that back in to the equation and see that it verifies the equation.